It fixes the biggest limitations of lithium-ion: energy density, charging speed, lifetime, and safety. But here's the reality. Until today, there are no vehicles in production using solid-state batteries. Not one. Not at scale, and not shipping to customers.
When an automaker claims it has developed a solid-state battery capable of 933 miles of range, operation at minus 22 degrees Fahrenheit, and energy densities of 600 watt-hours per kilogram, skepticism is not just reasonable, necessary. For more than a decade, the battery industry has repeatedly promised solid-state breakthroughs that were always 5 years away and rarely ready for real-world use. Today's best lithium-ion batteries barely exceed 300 watt-hours per kilogram, suffer cold weather range losses of over 30%, and still trade fast charging for faster degradation. Against this backdrop, Chery's claims appear to challenge established technical limits. So, how do solid-state batteries actually operate in electric vehicles? Welcome to the Tesla car world. If there is one lesson the battery industry has taught us over the past decade, it is this. Whenever a company claims it has built the perfect battery, the safest assumption is that something does not add up. We have watched this cycle repeat itself over and over again. That is precisely why the reaction to Donut Lab's solid-state battery was not irrational pessimism, but earned skepticism. A battery that supposedly offers 400 watt-hours per kilogram, charges in 5 minutes, lasts 100,000 cycles, works flawlessly in extreme temperatures, costs less than lithium-ion, and does not even use lithium would not be a normal technological improvement. It would be a scientific revolution. Yet, when the moment came to show real evidence, there were no working cells, no independent test data, no disclosed chemistry, and not even a single charging or discharging demonstration. At CES, the world's biggest stage for technological proof, all that appeared were empty battery shells. For anyone familiar with battery development, that alone was enough to raise serious doubts. The refusal to disclose even the basic chemical family of the battery, combined with repeated promises that proof was always just weeks away, followed a pattern the industry has learned to recognize all too well. This is why, when yet another set of astonishing solid-state battery claims began circulating, a solid-state battery with 600 watt-hours per kilogram, a 933 miles driving range, full performance at minus 22 degrees Fahrenheit, and deployment in real vehicles within a year sounds, at first glance, even more unrealistic than what Donut Lab was proposing. Importantly, because this time the claims are not coming from a small, opaque startup with no visible manufacturing footprint. They are coming from Chery, one of China's largest and most established automakers. A company that exports millions of vehicles globally, operates multiple international R&D centers, and already mass-produces electric vehicles at scale. That fact alone does not make the claims true, but it fundamentally changes the context in which they must be evaluated. Skepticism remains essential because solid-state batteries are not an easy problem that large companies simply forgot to solve. For more than a decade, industry giants like Toyota, Samsung, Panasonic, LG Energy Solution, CATL, and others have poured tens of billions of dollars into solid-state research. Yet large-scale commercialization has continuously been pushed back. Solid-state batteries are extraordinarily difficult to stabilize and even harder to manufacture consistently. The solid electrolyte must conduct ions efficiently, remain chemically inert, resist dendrite penetration, and maintain perfect interfacial contact with electrodes that expand and contract during cycling. Even microscopic defects can lead to rapid degradation or catastrophic failure. This is why solid-state batteries often perform well in laboratory cells but struggle when scaled up to automotive-sized formats. Against that backdrop, Chery's announcement naturally triggers suspicion. A 600 watt-hour per kilogram battery would be roughly double the energy density of today's best production lithium-ion cells, which typically sit in the 250 to 300 watt-hour per kilogram range. Such a jump would not merely improve electric vehicles, it would fundamentally change how they are used. Range anxiety, the single most persistent psychological barrier to EV adoption, would largely disappear. Long-distance travel would no longer require careful route planning, and cold weather performance, one of the greatest weaknesses of current EVs, would cease to be a major concern. What makes Chery's claim particularly provocative is the emphasis on performance at minus 30 degrees Celsius. Cold temperatures dramatically slow ion movement in liquid electrolytes, increasing internal resistance and slashing usable capacity. Many EVs lose 30 to 40% of their range in deep winter conditions. Chery is not merely claiming that its solid-state battery survives cold weather, but that it maintains reliable operation and high efficiency at temperatures where conventional lithium-ion systems struggle severely. If true, this alone would indicate a genuine materials-level breakthrough rather than a marketing exaggeration. The first critical difference between Chery's announcement and the Donut Lab story lies in transparency. Donut Lab refused to clearly define what its device actually was, leaving open the possibility that it was closer to a supercapacitor than a true battery. Chery, by contrast, has explicitly stated that its Rhino S battery is a solid-state battery using an oxide-based solid electrolyte. This may sound like a minor detail, but in battery science, it is anything but. Identifying the electrolyte class immediately anchors the technology within known physical principles, known challenges, and known performance ceilings. Oxide-based solid electrolytes are widely studied, known for their chemical stability and safety advantages, and considered one of the most promising long-term solid-state pathways, even though they are notoriously difficult to manufacture at scale. By publicly committing to the oxide route, Chery exposes itself to scrutiny from researchers and competitors alike. It is not hiding behind ambiguity or redefining terminology. This does not prove the battery works as claimed, but it does suggest that the company's not attempting to obscure the fundamental nature of the technology. The second major difference lies in industrial credibility and behavior. Chery is not presenting this battery as an overnight miracle destined for immediate consumer mass adoption. Instead, the company has outlined a phased rollout that begins with controlled fleet deployment in ride-hailing and rental services in 2026, followed by broader commercialization in 2027. This approach aligns closely with how complex, high-risk technologies are actually introduced in the automotive world. Fleets generate large volumes of real-world data under monitored conditions, allowing manufacturers to study degradation, thermal behavior, and failure modes before exposing the technology to millions of private owners. This measured rollout stands in stark contrast to the pattern seen in many overhyped battery stories, where companies promise instant mass production without acknowledging the immense challenges of scaling. It suggests that Chery understands the risks involved and is attempting to manage them rather than deny their existence. None of this means Chery's claims should be accepted at face value. There are still critical unanswered questions about whether the 600 watt-hour per kilogram figure represents a peak laboratory result or a realistic production-level cell, how the battery behaves under repeated fast charging, what the true pack-level energy density looks like, and how costs will evolve as production scales. Solid-state batteries are still expensive, and even optimistic estimates suggest they currently cost several times more than conventional lithium-ion systems. However, there is a crucial distinction that must be made. Unlike Donut Lab's claims, which appeared to contradict large portions of established battery science, Chery's announcement does not obviously violate known physical laws. It is aggressive, ambitious, and optimistic, but it exists within a framework that researchers have been working toward for years. The direction of solid-state development has consistently pointed toward higher energy densities, improved safety, and better thermal stability, particularly with oxide-based electrolytes. In the next phase of this analysis, we will examine the 600 watt-hour per kilogram claim in greater detail. Compare Chery's approach to the solid-state strategies pursued by companies like Toyota, Cattle, and Samsung, and explore why cold weather performance may be the strongest indicator that this technology is closer to reality than many previous Holy Grail battery stories. So, how does Chery's solid-state battery deliver 600 watt-hour per kilogram performance at 22 degrees Fahrenheit? If we take Chery's claims seriously, the first number that demands closer examination is the most provocative one of all, 600 watt-hours per kilogram. This figure sits so far above today's production batteries that it immediately triggers disbelief, and rightly so. But disbelief alone is not analysis. To understand whether this number belongs in the realm of science fiction or aggressive but plausible engineering, it must be placed in the context of where solid-state research has actually been heading over the past decade. Conventional lithium-ion batteries are constrained by the limitations of liquid electrolytes and graphite-based anodes. Even with advanced cathode chemistries and silicon-doped anodes, practical cell-level energy density has plateaued around 250 to 300 watt-hour per kilogram. Beyond that point, gains become marginal and trade-offs in safety, lifespan, or cost escalate rapidly. This is precisely why the industry has been searching for a fundamentally different architecture, rather than incremental improvements. Solid-state batteries are attractive not because they are easy, but because they remove several of the bottlenecks that define lithium-ion technology. The central promise of solid-state batteries lies in the use of lithium-metal anodes, which offer far higher theoretical capacity than conventional graphite. Their main obstacle has long been stability. In liquid electrolytes, lithium forms dendrites during charging that can cause short circuits and safety failures. Solid electrolytes are theoretically capable of suppressing dendrite growth while enabling much higher energy density, but scaling this concept beyond the laboratory has proven extremely difficult. Chery's approach reportedly relies on oxide-based solid electrolytes, which are chemically stable, non-toxic, moisture-resistant, and highly tolerant of extreme temperatures. These properties make them attractive from both safety and durability perspectives. However, oxides suffer from mechanical rigidity and poor contact with electrodes, resulting in high interfacial resistance and limited power output. Historically, these challenges have confined oxide-based solid-state batteries to research settings. Recent advances have begun to change this outlook. Research into composite oxide electrolytes, interface coatings, and nano-engineered structures has steadily reduced interfacial resistance while preserving stability. As a result, ultra-high energy densities, such as 600 watt-hour per kilogram, while still extremely challenging, now fall within a credible research trajectory. Notably, Chery's claim links energy density directly with cold weather performance, a condition that typically exposes battery weaknesses. If achieved, this would mark a significant departure from purely theoretical or marketing-driven claims. Chery's assertion that its solid-state battery maintains reliable operation at -30 degrees Celsius is therefore not a minor detail. It is arguably the strongest technical signal in the entire announcement. Solid electrolytes, particularly oxide-based ones, can offer more stable ion conduction across a wider temperature range than liquid electrolytes, which thicken or partially freeze in extreme cold. If Chery's battery truly performs as claimed at -30 degrees, it would indicate that ion transport and interfacial contact issues have been addressed to a degree that goes beyond laboratory demonstrations. This also explains why Chery repeatedly emphasizes cold weather performance, rather than focusing solely on headline range numbers. A company fabricating data would likely lean into ideal conditions and theoretical maxima. Emphasizing extreme cold, one of the most unforgiving environments for batteries, invites scrutiny rather than avoiding it. It suggests a degree of confidence that would be irrational if the technology were purely aspirational. Still, even if the underlying chemistry is sound, another question remains unavoidable: scaling. History shows that many solid-state batteries perform impressively in small cells, only to fail when scaled to automotive formats. Interfaces that behave acceptably in coin cells become unstable in large prismatic or pouch cells. Manufacturing tolerances that are manageable in the lab become unacceptably expensive on the factory floor. This is where Chery's industrial approach becomes crucial. Unlike startups that announce breakthroughs before building factories, Chery is integrating its solid-state battery into a real vehicle platform and planning controlled deployment through fleets. Ride-hailing and rental vehicles accumulate mileage quickly, operate in diverse environments, and provide rich data sets on degradation and failure modes. If Chery's battery struggles with longevity, thermal management, or charging stress, these fleets will reveal the problems far faster than limited consumer trials ever could. This approach implicitly acknowledges that first-generation solid-state batteries may not be perfect, but can still be commercially valuable if managed correctly. There is also the matter of performance beyond the battery itself. Chery pairs the solid-state system with an 800-volt architecture and a high-speed electric motor capable of reaching 30,000 revolutions per minute. None of this is revolutionary on its own, but it is consistent with a vehicle designed to exploit high power density and fast charging. An 800-volt system reduces current for a given power level, lowering heat generation and enabling faster charging without excessive losses. In other words, the vehicle architecture aligns with the battery's claimed strengths rather than contradicting them. At this point, the contrast with the Donut Lab story becomes unavoidable. Donut Lab presented numbers that appeared detached from any clear system-level design, with no visible pathway from laboratory claim to vehicle integration. Chery, by contrast, is embedding its battery into a coherent vehicle platform with defined electrical architecture, performance targets, and deployment strategy. This does not eliminate the risk of overpromising, but it does ground the claims in an industrial reality that Donut Lab never demonstrated. Cost, however, remains the most fragile part of the narrative. Solid-state batteries are currently expensive, with some estimates placing them at nearly 3 times the cost of liquid lithium-ion batteries. Chery has not denied this. Instead, it has effectively deferred the cost question by limiting early deployment to fleets and premium segments. This is a familiar strategy in automotive history. New technologies almost always debut at the high end of the market, where margins can absorb higher costs and early adopters are more tolerant of imperfections. If costs decline with scale and process optimization, broader adoption follows. If they do not, the technology remains niche. What matters here is that Chery is not claiming to have magically eliminated cost trade-offs. It is acknowledging them implicitly through its rollout strategy. That alone separates this announcement from the kind of hype that collapses under minimal scrutiny. Of course, skepticism remains justified. Independent validation will ultimately determine whether Chery's solid-state battery is a genuine breakthrough or an optimistic interpretation of early results. But unlike many past announcements, this one does not rely on secrecy, ambiguity, or unrealistic timelines. It aligns with known research directions, acknowledges real-world constraints, and places the technology within a credible industrial framework. This is why the Chery story deserves a different kind of attention. Not excitement without evidence, and not dismissal based on fatigue from past disappointments, but careful observation. If the fleet deployments in 2026 begin producing real-world data that supports even a fraction of these claims, the implications for electric vehicles would be profound. It would not mean that internal combustion engines disappear overnight, nor that every automaker is instantly obsolete, but it would signal that the long-promised solid-state future is no longer theoretical. From a manufacturing standpoint, Chery's solid-state battery effort stands out not because it claims laboratory success, but because it openly acknowledges the constraints of industrial reality. Unlike many battery announcements that focus exclusively on cell-level breakthroughs, Chery has framed its Rhino S solid-state battery as a system designed from the beginning with scalability, yield control, and vehicle integration in mind. This distinction is critical. In battery manufacturing, the difference between a promising prototype and a viable product is measured not in performance metrics, but in production consistency, defect rates, and cost convergence over time. Chery has confirmed that its solid-state batteries are being developed using an oxide-based electrolyte pathway, widely regarded as the most manufacturable of the 3 dominant solid-state approaches. While sulfide electrolytes offer higher ionic conductivity, they require extremely strict moisture control and specialized production environments, driving up cost and complexity. Polymer-based systems, on the other hand, tend to struggle at room temperature and below. Oxide electrolytes sit in a pragmatic middle ground, mechanically stable, chemically robust, and compatible with modified versions of existing lithium-ion production equipment. So what do you think about Chery's solid-state battery? Is it more convincing to you than Donut Lab's battery? Please share your opinion in the comments section below this video. Thanks for watching our video. Subscribe now so you don't miss the next breaking Tesla update. It's coming in just 2 days. If you want to explore more exciting information about Tesla EV or Tesla Bot, don't forget to hit the like button and share this video. Also, make sure to turn on notifications so you never miss our latest videos.
It's great to see US companies finally taking action to push the battery industry to the next level. We all know the truth. Batteries have long been the weakest link in the electric vehicle world. Not the design, not the range, but the cost of manufacturing and replacing them. Ask any car salesperson, and they'll likely dodge the question. Why? Because no one has managed to bring battery replacement costs down to a level consumers can afford. But now, the 24-megawatt semi-solid-state battery claims to do just that, thanks to its simplified design with semi-solid-state cells, fewer components, and sandwich-style assembly. The result? Lower fire risk, easier recycling, a remarkably low cost of just 6 cents per watt-hour, and the ability to fully charge in just 4 minutes. But the lab is easy to talk about. Mass production is the real test. Charge-discharge cycles must be validated with real-world data, and few manufacturers are willing to openly discuss battery degradation. But if 24 million can prove its durability, U.S. electric vehicles may finally break free from dependence on Asian battery suppliers, and budget-friendly models like the 11,800 BYD Seagull or the 24,400 XPeng G6 long range will never be a threat to the American EV market. Could this finally be the tipping point for the U.S. to lead in battery manufacturing? Welcome to Tesla Car World. Today, we're taking a closer look at the semi-solid-state lithium-ion battery technology developed by 24M. 24M, short for 24 Molecules, is a battery technology firm headquartered in Cambridge, Massachusetts, USA. They've distinguished themselves with a unique semi-solid platform engineered to tackle the four biggest challenges in the battery industry: driving down costs, boosting safety, increasing energy density, and maximizing recyclability. So how does 24M's semi-solid battery turn the 6 cents per watt-hour price into reality? This $0.06 per watt-hour claim is universally regarded as an extremely dubious assertion, lacking rigorous scientific evidence, a solid verifiable foundation, or validation. Any basic market observer with even minimal awareness also knows that current lithium-ion battery pack prices sit at approximately $115 per kilowatt-hour, means $0.115 per watt-hour. So a $0.06 per watt-hour headline rate implies a massive 48% discount over the already optimized current costs, a proposition that remains entirely questionable, implausible, and unfeasible with today's global battery manufacturing technology at scale. Even leading battery scientists and seasoned market research experts in their most optimistic and cited projections only anticipate that average global battery pack prices will gradually decline to below $100 per kilowatt-hour by the year 2025. So where does $0.06 per watt-hour figure come from? And why is 24 Million's battery able to accomplish this feat? Remember back at Battery Day, 2020. Elon Musk and Tesla consistently pursued dramatic cost reduction and significantly enhanced battery performance, publicly targeting an ambitious $60 per kilowatt-hour goal at Battery Day, 2020. And just 5 years later, that ambitious goal has fully materialized in published data, and we believe this extremely low price point derives from large-scale research experiments, because realistically, it would be nearly impossible to achieve at an internal or pilot production scale. Imagine a battery factory as a construction site where, instead of laying 20 painstaking rows of tiny bricks, brick, mortar, workers now install a few massive precast panels that raise the full height of the wall in a single lift. That is essentially what 24M's semi-solid process does. It cuts the number of individual placements in half, wiping away hours of labor and slashing the energy bills that normally keep the lights, ovens, and precision robots humming. Because each panel is poured as one dense slab, it ends up twice as thick as a traditional brick layer, so the same concrete footing supports far more material. Pay for the foundation once, carry double the load, and the cost per square foot, or per watt-hour, plummets. The advantage compounds inside the car itself. Where a typical electric SUV hides hundreds of brick-sized cells under the floor, 24M replaces that clutter with half a dozen wall-sized sheets, the company's so-called carpet cells. Fewer parts mean fewer welds, wires, screws, and cooling plates, which quietly chip 10 to 15% off the final bill while also removing dozens of potential failure points. The streamlined approach even reshapes the factory. With less real estate and equipment to finance, the company can build a plant for roughly half the cost, then pass the savings straight to automakers. This battery can run iron-based LFP powders, high nickel blends, or even future sodium chemistries without ripping out its tooling. That agility shields pack prices from wild swings in metal markets, and it shows up where it matters most. A 75 kilowatt-hour battery that costs about $8,600 today could fall to roughly $4,500. Couple that drop with a $7,500 federal credit and a mid-size electric crossover can undercut a gasoline SUV right on the showroom floor. Because the panels are cast in Massachusetts, the pack also clears new rules that penalize Chinese components, so more models stay eligible for incentives. Best of all, the same design that makes the battery cheap lets it add 200 miles of range in 4 minutes and keep working in -40-degree winters. So, how can they prove that a 4-minute charging time isn't just hype? It's an undeniable fact that even the most advanced semi-solid-state batteries on the market today can only charge from 15% to 90% in up to 18 minutes. Likewise, CATL's publicly announced fastest charging technology delivers 320 miles in just 5 minutes, but it doesn't achieve a full 100% charge in one session. And, as everyone knows, Tesla's cutting-edge superchargers still require 15 minutes to add 200 miles. You might not believe it, yet take a look. CATL has just unveiled its second-generation Shenzhou battery, capable of providing 323 miles, 520 kilometers of range in only 5 minutes of charging. That extra minute's difference shows that a 4-minute boost is not only feasible, but entirely within reach. If there's one thing that still holds people back from switching to electric vehicles, it's not the range, it's the charging time. But what if you could charge 200 miles of range in just 4 minutes? And you don't need a custom-built megawatt charging station. Unlike traditional lithium-ion batteries or even solid-state designs, this batteries use a proprietary electrolyte known as eternalite. While the company is understandably secretive about the details, after all, revealing too much could mean handing the keys to competitors. What's publicly known is already jaw-dropping. Eternalite has 3 times the ionic conductivity of standard electrolytes. That means ions, the tiny charge carriers that flow between the anode and cathode, can move way faster, resulting in dramatically shorter charging times. According to internal testing, 24M cells can add 200 miles of range in under 4 minutes, and they don't require exotic hardware to do it. Unlike other fast-charging batteries that rely on 1 megawatt ultra-high-power chargers, which are expensive, rare, and often require special infrastructure, 24M's battery charges just fine on standard 400-volt and 800-volt platforms. That means no major overhauls to the grid, no custom cooling systems, just plug in and go. That alone is revolutionary. But it gets even better. Thanks to the Eternalite electrolyte, 24M's batteries perform incredibly well in cold environments, one of the Achilles heels of most lithium batteries. Standard lithium-ion cells lose 25 to 30% of their capacity at 0 degrees Celsius and perform terribly at -20 degrees Celsius. But Eternalite keeps on going. In testing at -40 degrees Celsius, 24M cells maintained over 80% of their capacity and full energy transfer. That's virtually unheard of, and it makes these batteries perfect for cold weather markets like Canada, Northern Europe, or even military operations. Think about how we refuel gasoline cars. A typical gas stop takes about 5 minutes. Until now, EVs just couldn't compete with that. You had to plan your routes around charger availability and wait times. But with this tech, the EV charging experience becomes just as fast and convenient as gas, maybe even faster. More exciting, this performance doesn't come at the expense of cost or safety. In fact, the fast charging capability is a direct result of the chemistry, not brute force. Eternalite enables high current flow without overheating, and it pairs with 24M's proprietary Impervio separator to prevent the risk of thermal runaway. This means faster charging without the fire hazard that often plagues high-speed charging designs. By eliminating the traditional bottlenecks of charging time and cold weather performance, 24M is knocking down 2 of the biggest walls blocking widespread EV adoption. And the fact that this can be done without exotic infrastructure means the path to mass deployment is wide open. So, why can it kill China's LFP technology? We must acknowledge that China currently controls more than 80% of global LFP battery production. At the same time, LFP batteries accounted for 82.8% of all battery installations in China in April 2025, and CATL and BYD remain the industry giants, holding 38% and 17.2% of the worldwide market, respectively. Besides, we've probably heard all the buzz around solid-state batteries, how they're the next big thing, promising higher energy density, better safety, and longer lifespan. But they also come with sky-high costs, slow manufacturing ramp-ups, and persistent issues with degradation. Rather than go down the solid-state route, 24M has developed something entirely different: semi-solid lithium-ion batteries. This simplified process opens the door to thicker electrodes, meaning higher energy density and longer range per charge. In lab testing, 24M's batteries have achieved a stunning 660 watt-hour per kilogram, far beyond the 400 watt-hour per kilogram mark that's considered transformative for aerospace, high-performance EVs, and electric vertical takeoff and landing aircraft. But great design isn't just about performance, it's about solving real-world pain points, and 24M does that with recyclability and safety in mind, too. Let's talk about recycling, one of the biggest bottlenecks in the battery industry. Most lithium-ion batteries today require harsh chemical processes to recover usable materials, costly, inefficient, and environmentally damaging. But, thanks to 24M's Life Forever architecture, there's a smarter way. Because the electrodes are free from binders and formed in thick cast layers, they can be mechanically separated at end of life. No fire, no acid baths, no black mass. This allows for up to 98% material recovery, all through a clean and scalable process. It's a true step toward a closed-loop battery economy, easier thermal management. It's simpler, safer, and reduces system costs by an estimated 30% per kilowatt-hour. Even better, it scales. Manufacturing is already semi-automated and production-ready, paving the way for rapid adoption. And it's made in America, ready to challenge not just the limits of what's possible, but also the global supply chain that's long held the EV industry hostage. What do Elon Musk and Tesla say about this semi-solid state battery? With all the standout advantages discussed, ranging from higher energy density and improved safety to scalable, cost-effective manufacturing, it's no surprise that semi-solid state batteries are starting to attract attention from major players in the EV industry. But what about Tesla and Elon Musk, the names synonymous with cutting-edge innovation? What do they have to say about semi-solid state batteries? And more importantly, have they started using them? Surprisingly, Elon Musk has never publicly endorsed semi-solid state batteries the way he's hyped solid-state batteries in the past. In Tesla's Battery Day presentations and recent investor briefings, the focus remains on the company's 4680 battery cells, a next-gen version of traditional lithium-ion technology. There's been no official mention of semi-solid-state batteries as part of Tesla's core development strategy. However, just because Elon isn't talking about it doesn't mean Tesla isn't paying attention. As with many disruptive technologies, Tesla tends to test and experiment behind the scenes, and only goes public once a solution is close to commercial viability. Some industry rumors suggest Tesla may have explored partnerships with US-based semi-solid battery startups, but ultimately walked away due to material cost concerns at the time. It's worth noting that Musk's philosophy has always focused on scalable practicality, meaning a technology not only has to work, but it must be mass-producible at a reasonable cost. Solid-state batteries, for all their promise, still struggle in that department. Semi-solid batteries, on the other hand, are inching closer to meeting those real-world requirements. At this point, Tesla has not yet deployed semi-solid state batteries in any commercial vehicles, but key Tesla suppliers, particularly Panasonic and CATL, are actively investing in hybrid battery technologies, including semi-solid variants. This suggests that Tesla is keeping the door open, especially as competitors like NIO and Toyota have already announced plans to pilot semi-solid batteries in long-range electric vehicles. Elon Musk once famously said, "Solid-state batteries sound great, but they're insanely hard to manufacture at scale. That's why we're focused on tech we can build now." While he wasn't referring directly to semi-solid batteries, his words inadvertently support the semi-solid approach,
which bridges the gap between current-gen lithium-ion and fully solid-state designs. It's safer, more flexible, and far more viable for mass adoption. Some industry analysts believe that in the coming years, as Tesla maxes out the potential of the 4680 and the pressure to improve weight, range, and energy density intensifies, they'll be forced to revisit semi-solid-state batteries as a logical next step. So, while Tesla hasn't made a move yet, one thing's clear: Elon Musk is watching. And with the current pace of innovation, it wouldn't be surprising if Tesla suddenly announced a future Model 3 or next-gen Roadster powered by semi-solid batteries, built on a quiet partnership already in the works. It's an inevitable choice, if not a leading-edge trend in technology, because in just a few years, when the Earth's average temperature climbs close to 113 degrees Fahrenheit, you'll realize just how vital electric vehicles really are. It's no coincidence that governments around the world are actively promoting EV adoption and offering generous incentives like the $7,500 federal tax credit in the US, a prime example. It's a smart policy, but it brings with it a significant challenge: the looming scarcity of critical materials used in lithium batteries. Supply simply won't keep up. Do you think Tesla will eventually ditch solid-state dreams and pivot to semi-solid-state batteries, especially if they're cheaper, safer, and faster to charge? Why hasn't Elon Musk jumped on this yet? Please share your opinion in the comment section below this video. Thanks for watching our video. If you want to explore more exciting information about Tesla EV or Tesla Bot, don't forget to hit the like button and share this video. Also, make sure to subscribe to Tesla Car World and turn on notifications so you never miss our latest videos. As we all know, in today's EV race, low price is an advantage, but performance is the crown. For a long time, there have been many rumors that Tesla would use sodium-ion batteries that require no lithium, no cobalt, and no nickel for its future strategic models. With raw material costs, 30–40% lower sodium-ion batteries have been seen as the golden key to the affordable car Elon Musk has mentioned many times. However, that scenario now seems unlikely due to the major drawbacks of sodium-ion batteries, issues that even Tesla has not been able to overcome. As a result, Elon Musk's latest decision has confirmed that the 4680 lithium battery will be the only future, as Tesla has just solved the biggest barrier facing this battery type. This means sodium-ion batteries will have no chance of making their way into Tesla EVs. So what disadvantages led Elon Musk to reject sodium-ion batteries despite their potential? Let's find out now. If you've followed Tesla for a long time, you'll notice that every product from Elon Musk revolves around one ultimate goal: optimizing the balance between performance and cost. You know, people often say that Tesla products are priced higher than the market, but when you look at the performance features and technology, it's clear that the balance is nearly perfect, arguably even more affordable for what you get. Yeah, it's no coincidence that the Model Y and Model 3 consistently rank among the best-selling vehicles in many major markets. That said, it's impossible to deny the fact that Tesla still doesn't have a model priced under $30,000. Elon Musk has repeatedly hinted at a more affordable car around $30,000, but it clearly hasn't materialized yet. There are many reasons for this, but we believe the battery is the biggest barrier to a truly low-cost vehicle. Last year, there were widespread rumors that Tesla would use sodium-ion batteries for the affordable model Elon Musk had promised. This made perfect sense, since sodium is abundant and significantly cheaper than lithium-ion batteries, an ideal weapon to turn the dream of a mass-market EV into reality. However, the harsh truth is that this will never happen. The decisive reason Tesla chose to reject sodium-ion batteries and instead bet everything on the 4680 lithium-ion battery is the unbridgeable gap in energy density. Energy density is the gold standard that determines how far an electric vehicle can travel and how much it weighs. While sodium-ion batteries have a cost advantage, their energy density is relatively modest, currently hovering around just 140–160 watt-hours per kilogram. By contrast, Tesla's 4680 battery cells are targeting and have already reached levels of 240–300 watt-hours per kilogram. This difference isn't just a matter of numbers on a spec sheet. It's the line between a true electric vehicle and a short-range city car. Why is energy density so critical to Tesla? Imagine if Tesla equipped the Model 3 with sodium-ion batteries. To achieve a driving range of 300 miles, the battery pack would need to be 1.5 to even twice as heavy as a lithium-based pack. That extra weight creates a negative spiral.
A heavier car wears out tires faster, requires reinforced suspension, and most importantly needs more energy just to move its own mass. This runs completely counter to Elon Musk's design philosophy of minimalism and efficiency. In contrast, the 4680 battery is not simply a larger cell. With a diameter of 46 mm and a height of 80 mm, it has 5.5 times the volume of previous cells, allowing it to hold far more active material. Combined with the tabless design, Tesla has solved the thermal management problem, the biggest obstacle when increasing battery size. Thanks to its superior energy density, Tesla can integrate the battery directly into the vehicle's chassis as a structural battery pack, reducing overall vehicle weight by 10% and increasing range by 16% without taking up additional space. Moreover, Elon Musk understands that Tesla customers buy the brand for the combination of fast-charging technology and strong acceleration. Sodium-ion batteries with their lower energy density would leave the car feeling underpowered during hard acceleration and struggling to maintain performance at high speeds. The 4680 lithium-ion battery with its dense energy storage can deliver massive power, instantly preserving Tesla's performance crown. Beyond its disadvantage in energy density, another critical weakness that led Tesla to rule out sodium-ion batteries is the pressure of fast charging and structural lifespan. For an ecosystem built on speed and durability like Tesla's, sodium-ion batteries reveal chemical shortcomings that even the most advanced battery management software can hardly compensate for. First, let's talk about the challenge at supercharger stations. Tesla takes pride in charging capabilities that add hundreds of miles of range in just 15-20 minutes. To achieve this, ions must move extremely fast between the battery's two electrodes. However, sodium ions are about 25–30% larger than lithium ions. Imagine trying to push basketballs through a narrow hallway. Instead of tennis balls, the resistance and friction would be far greater. Under the high current of fast charging stations, these larger sodium ions not only move more slowly, but also generate extreme heat buildup. If Tesla were to use sodium-ion batteries, it would have to significantly reduce charging power to avoid the risk of fires or explosions. This would directly undermine the charge as fast as refueling experience that Elon Musk has worked so hard to build. Second is the issue of cycle life and physical stability. This is where sodium's size disadvantage becomes a true structural destroyer for the battery. With every charge and discharge, ions insert into and exit the crystal lattice of the electrodes, a process known as intercalation. Because of their oversized nature, sodium ions cause far more expansion and contraction than lithium ions. After just a few hundred cycles, this kind of mechanical torture leads to cracking and degradation of the electrode structure, resulting in rapid battery degradation. While Tesla's 4680 lithium batteries are engineered to withstand thousands of charge cycles, today's sodium-ion batteries often show noticeable degradation after a relatively short period of high-intensity operation. For an automaker like Tesla, which offers long-term battery warranties, adopting a technology that ages quickly like sodium-ion would be a disaster in terms of maintenance costs and customer trust. According to recent information we've received in just the past year alone, 3 major sodium-ion battery companies have shut down. Another voluntarily returned $9 million to investors despite possessing the practical technology. And yet another faced a $25 million inventory buildup that couldn't be shipped when the company collapsed. What is strangling these companies is not a technical failure but a classic case of bad timing. Specifically, while sodium-ion technology has been struggling to move from the lab to mass production, global lithium prices have plunged by as much as 90%. This dramatic drop has caused sodium's biggest competitive advantage, its lower cost, to all but evaporate. Finally, Tesla's recent breakthrough in overcoming the biggest barrier facing the 4680 battery with dry electrode technology delivered the decisive blow to sodium-ion batteries. Tesla has found a way to drive lithium battery production costs down to record lows without sacrificing performance. Throughout the 2020-2023 period, Tesla fell into what it called production hell, having only mastered the dry process for the anode, while the cathode still relied on the traditional wet process. This unintentionally resulted in an inefficient hybrid battery, forcing the company to maintain massive drying ovens and toxic solvent handling systems, completely wiping out the promised advantages in cost and factory footprint. As a result, early generation 4680 batteries suffered from low energy density, high production costs, and were deployed only in limited numbers on the Cybertruck for real-world testing. However, by early 2026, Tesla achieved a historic turning point by fully mastering the dry electrode process for both the anode and cathode at industrial scale. This was an extraordinarily difficult engineering achievement, eliminating toxic chemical solvents entirely, along with energy-hungry drying ovens. The innovation not only reduced factory floor space by up to 90%, but also optimized the battery's physical structure. By cutting binder content down to about 1%, Tesla freed up room for more active material, boosting energy density by 5–10% without changing the core battery chemistry. Crucially, the tabless design enables more even current distribution, reduces heat generation, allows stable fast charging, and extends battery life to as many as 2,000 charge cycles while still retaining 90% of capacity. The success of dry electrode technology has delivered enormous strategic benefits. The 4680 battery is now cheaper to produce than the 2170 battery in the United States, allowing Tesla to confidently bring it back to its core Model Y lineup and prepare for future lower-cost vehicle variants. More importantly, domestic battery production gives Tesla a strategic shield against tariff risks and global trade tensions. Instead of relying on external suppliers, Tesla can now control the entire value chain from battery cells to vehicle structure, strengthening its self-sufficiency and reducing long-term supply chain risks. Although in theory, sodium as a raw material is roughly 20 times cheaper than lithium due to its natural abundance, this advantage is entirely offset by today's operational realities. Tesla and its partners' lithium battery factories have undergone decades of optimization, achieving near-ideal operational efficiency of up to 99%. By contrast, sodium-ion production would require building an entirely new ecosystem involving massive upfront capital investment. At the same time, lithium carbonate prices have collapsed, falling from a peak of $70,000 per ton to below $10,000 per ton. This has narrowed the cost gap between the two chemistries to the point where sodium no longer offers enough economic incentive for Tesla to risk disrupting its 4680 production lines, which are only now reaching maturity. An extremely important but often overlooked factor is recyclability and life cycle value. For Tesla, a 4680 battery does not reach the end of its life when the vehicle is retired. Instead, it is treated as a mobile open-pit mine. Thanks to their high nickel and lithium content, used 4680 packs retain significant economic value in recycling. Modern lithium-ion recycling technology can recover 90–95% of critical metals, effectively turning every retired vehicle into a raw material source for the next generation of cars. This forms the foundation of Tesla's closed-loop manufacturing strategy, reducing dependence on new mining while reinforcing its identity as a sustainable technology company. Sodium-ion batteries, however, face an economic paradox. Because sodium is so cheap and abundant, end-of-life sodium batteries have virtually no recovery value. This removes incentives for recyclers to invest in processing technology, effectively turning sodium-ion into a long-term industrial waste problem. For a brand so closely associated with environmental responsibility and the circular economy, choosing a use and discard battery technology would not only represent a strategic step backward, but also pose a serious reputational and social responsibility risk. Another aspect frequently highlighted in sodium-ion marketing campaigns is safety. Chemically speaking, it is true that sodium is less violently reactive than lithium. However, Tesla has fundamentally changed the game through the physical architecture of the 4680 cell. Thanks to its tabless design, localized hotspots, the primary trigger for thermal runaway, are largely eliminated. Current is distributed more evenly, heat generation is reduced, and thermal management becomes far more controllable. Rather than relying solely on chemistry, Tesla addresses safety at the cell architecture level. Beyond that, the 4680 battery is engineered to function as part of the vehicle's structural framework, a concept known as a structural battery pack. With its thick, rigid casing, each cell does more than store energy. It actively contributes to load bearing and increases overall torsional stiffness of the vehicle body. In crash tests, this battery structure effectively acts as an armored layer protecting occupants. By contrast, today's sodium-ion batteries primarily exist in pouch or thin shell formats, well suited for stationary storage or low-cost vehicles, but incapable of serving a structural role at the chassis level, comparable to the 4680. At an even deeper level of electrical engineering, there is a detail that only powertrain engineers tend to focus on: the voltage discharge curve. Sodium-ion batteries exhibit a much steeper voltage drop as state of charge declines. When the battery falls to around 50%, its voltage is already significantly lower than at full charge. This creates a major challenge for inverters and electric motors, which are optimized to operate within a stable voltage window. The result is a noticeable loss of power at lower charge levels, causing sodium-ion vehicles to feel underpowered and inconsistent, degrading the driving experience. By contrast, Tesla's 4680 lithium battery maintains a relatively flat voltage curve throughout the discharge cycle. This allows Tesla vehicles to deliver nearly consistent acceleration and performance, whether the battery is at 80% or down to just 20%. This is the key factor behind the feeling that a Tesla is always strong, a core piece of DNA in the Tesla driving experience. Switching to sodium-ion would almost certainly break this characteristic. That said, this does not mean sodium-ion is a failed technology. CATL, the company that now holds a dominant position in both EV batteries and energy storage, has officially brought sodium-ion into commercial production. Most recently, it introduced the Tianqing sodium-ion battery with an energy density of 175 watt-hours per kilogram, a lifespan of up to 100,000 charge cycles, and the ability to retain 90% usable capacity at extreme temperatures as low as 40 degrees Celsius. Even more impressively, the battery can be charged immediately even when completely frozen at 30 degrees Celsius. Clearly, CATL is taking sodium-ion very seriously despite its inherent limitations. What makes this development significant is not that sodium-ion is new, but that CATL has chosen to stand behind it. In an industry where capital intensity, market confidence, and manufacturing scale determine almost everything, CATL's serious commitment instantly changes how the world views sodium-ion technology. What's interesting is that while CATL continues to move forward, much of the global sodium-ion ecosystem is pulling back. Many startups once hailed as the post-lithium future have quietly disappeared, some even slipping into bankruptcy without much notice. Others were forced to return capital to investors as market sentiment turned against them. This creates a paradox if sodium-ion is truly a dead end. Why would CATL, the company with the deepest understanding of batteries, continue to invest in it? The answer is this: CATL does not view sodium-ion as a replacement for lithium, but as a complementary pillar within a multi-layered energy ecosystem. In their vision, the future does not belong to a single battery chemistry, but to a clear differentiation of technologies, each serving a distinct role. For years, the battery industry has been over-reliant on lithium to the point where any fluctuation in price, geopolitics, or supply chains can send shockwaves through the global market. CATL understands this risk better than anyone because it operates massive supply chains spanning raw material extraction all the way to cell manufacturing. Sodium-ion, with its extremely abundant and geographically widespread raw materials, offers a strategic advantage that lithium simply cannot. Reduced exposure to geopolitical choke points. CATL's persistence with sodium-ion, therefore, is not just a technology story, it is a story about energy security. In an increasingly unstable world where sanctions, trade wars, and regional conflicts can disrupt supply overnight, owning a battery technology that does not depend on lithium, cobalt, or nickel becomes an invaluable form of strategic insurance. More importantly, CATL is not just talking about sodium-ion on paper. It is actively building an entire ecosystem around it, from safety standards and national certifications to real-world deployment and integration. Once a technology is brought to market at industrial scale, it crosses the boundary of the laboratory and enters a phase of real-world validation. That is precisely what makes CATL's sodium-ion efforts noteworthy, even as the broader market remains hesitant. Sodium-ion is not a recent invention. In fact, it is one of the earliest electrochemical battery research paths developed almost in parallel with lithium-ion. Its surge in attention over the past decade reflects economic and strategic factors rather than any fundamental scientific limitation. As early as the 1970s, when scientists began searching for energy storage solutions for a post-oil future, sodium was already considered a serious candidate. The logic was straightforward. Sodium sits right next to lithium on the periodic table, shares similar chemical properties, and most importantly exists in near limitless supply. Early sodium-ion research emerged in the United States, Europe, and Japan at roughly the same time as the first lithium battery experiments. In many laboratories, sodium was even viewed as the more resource-rational option. History, however, took a different path. When lithium-ion batteries achieved key breakthroughs in the 1980 and 1990, particularly with the development of suitable anode and cathode materials, lithium rapidly pulled ahead in terms of commercial viability. Its smaller ionic radius allowed lithium to work efficiently with common materials like graphite, while sodium struggled with structural compatibility at the material level. As a result, the vast majority of global research funding, investment, and manufacturing capacity shifted toward lithium, and sodium-ion was gradually relegated to a secondary role within academic research. So, do you think sodium-ion batteries are finally ready for real-world adoption, or is it still too early? And that's where we'll leave it for today. Sodium-ion isn't about hype, it's about timing and strategy. If you enjoyed this deep dive, hit like, subscribe, and share your thoughts below. Your support really helps the channel grow. See you in the next one.